Before we begin tonight, I want you to look at your hand just for a moment. Look at it. That hand, your hand is made of atoms, approximately 7 octillion atoms. 7 octillion atoms, give or take, each one mostly empty space. The nucleus of an atom is so small compared to the atom itself that if you enlarged an atom to the size of a football stadium, the nucleus would be a grain of sand at the center, and everything else, all the rest of the enormous space inside the atom would be empty, with electrons somewhere in that space, in orbits that are not really orbits, in positions that are not really positions, moving in ways that quantum mechanics says cannot be fully known, even in principle. Your hand is mostly nothing, and yet you can feel it, touch things with it, hold things, build things, love people with it. The emptiness doesn't seem to be a problem. Tonight I want to talk about why, about what physics actually says the world is made of, about what the rules of the universe actually are. Not the high school version, the real version, the one that, when you sit with it long enough, changes something in how you see everything. Before we go in, tell me where you are right now. What country, what city, what time it is. Drop it in the comments before you fall asleep. I love knowing where these quiet, curious, nighttime minds are. Now, let's start at the beginning. Kinematic. There is a set of rules that the universe follows every time, without exception, without negotiation, without preference. They don't care who you are or where you are or what you believe. In a galaxy 13 billion light years away, the same rules apply. In the core of a neutron star, where matter is compressed to impossible densities, the same rules apply. In the quantum world, smaller than any instrument is ever directly measured, the same rules apply. We call them the laws of physics. But that name is misleading. A law sounds like something that could be broken, something that was decided by someone and could be decided differently by someone else. These are not that kind of law. These are not rules that were imposed. They are descriptions of how reality actually behaves. The best descriptions, that 400 years of the most rigorous, most careful, most self-correcting, intellectual project in human history has been able to produce. And what those descriptions say about the world is stronger, more beautiful, more counterintuitive than almost anything fiction has ever invented. Tonight, I want to walk through those descriptions slowly, carefully, letting each one settle before we move to the next, because each one deserves that. Each one is the product of centuries of work by extraordinary minds who gave everything to understand what the world actually is, what physics actually is, the project of understanding reality. Physics is the attempt to describe reality at its most fundamental level, not the level of biology, where we describe organisms, not the level of chemistry, where we describe molecules and reactions, not the level of geology, where we describe rocks and plates. The level beneath all of that, the level of particles and forces, of space and time, of energy and matter, and the relationships between them. Physics asks the deepest questions. That can be asked: what is matter made of? What is time? What is space? Why does gravity pull? Why does light travel at a specific speed? Why are there forces? What are forces? What would the universe look like if the constants of nature were different? Is there a single theory that describes everything These questions sound philosophical. They are, but physics is different from philosophy in one specific way. Physics doesn't just ask the questions, it answers them with experiments, with measurements, with the hard, specific, falsifiable predictions that can be tested against reality. And the answers are not simple. They are not comfortable. They are not what we would have designed. If we were designing a universe, the electron doesn't orbit the nucleus the way the planets orbit the sun. It doesn't have a definite position until it is measured, and measuring it changes it. Time doesn't flow at the same rate. For everyone, it passes more slowly. For someone moving fast or near a massive object than for someone stationary. In empty space, space itself bends, curves, stretches, in the presence of mass and energy in ways that affect every path through the universe, including the path of light. These are not metaphors. They are the actual descriptions that physics has arrived at after centuries of measurement and theory and experiment and the ruthless rejection of anything that doesn't match what reality actually does. What physics has found is essentially this. At the largest scales, the universe is described by general relativity, Einstein's theory of gravity and space-time that describes how mass curves space and how curved space affects the motion of everything in it. At the smallest scales, the universe is described by quantum mechanics and its extension, quantum field theory, which describes particles as excitations of fields that fill all of space and govern the behavior of everything. Below a certain scale are the intermediate scales, classical physics, Newton's mechanics, Maxwell's electromagnetism, the thermodynamics of heat and energy, gives excellent descriptions of the world we can directly experience. The great unresolved problem of physics is that general relativity and quantum mechanics are both extraordinarily successful in their respective domains, but they are mathematically incompatible. They cannot both be right as fundamental descriptions of reality, at least not in their current forms. The unification of quantum mechanics and gravity is the central unsolved problem of theoretical physics, the project of finding a theory that correctly describes both the very large and the very small, that reduces to both general relativity and quantum mechanics in their respective limits, is the deepest intellectual challenge that physics currently faces. Tonight, we're going to explore both. The world as general relativity describes it, and the world as quantum mechanics describes it, and the extraordinary strangeness of what both say about the nature of everything, the atom, mostly nothing. Everything starts with the atom, or rather with the discovery that everything is made of atoms, and then with the further discovery that atoms themselves are made of things, and that those things are stranger than anything the people who discovered them had been prepared for. The ancient Greeks speculated that matter might be made of indivisible particles. Democritus, around 400 BCE, proposed the theory of atoms. Atomos in Greek means indivisible, the thing that cannot be cut, the smallest possible piece of matter. He was right in spirit, wrong in detail. As it turned out, atoms can be divided into a nucleus and electrons. The nucleus can be divided into protons and neutrons. Protons and neutrons can be divided into quarks, and whether quarks themselves can be divided is still an open question. But the spirit was correct. Matter is not infinitely divisible. There are constituent parts that make up everything, and those parts have specific properties that determine the properties of everything made from them. The structure of the atom, the modern picture of the atom, emerged over several decades in the late 19th and early 20th centuries through a series of experimental discoveries, each one more surprising than the last. J.J. Thomson discovered the electron in 1897 by showing that cathode rays were made of particles much lighter than any atom with a negative electric charge. The electron was the first subatomic particle discovered. Ernest Rutherford showed in 1911 that the positive charge of an atom was concentrated in a tiny, dense nucleus at the center, rather than spread uniformly through the atom, as Thomson's plum pudding model had proposed. His experiment was simple and devastating. He fired positively charged alpha particles at a thin gold foil and measured where they went. Most went straight through, as expected, but a small fraction bounced back at large angle, even directly backwards. This was shocking. If the positive charge was spread through the atom, no alpha particle should bounce back. They would just be deflected slightly by the diffuse charge distribution. But if the positive charge were concentrated in a tiny nucleus, a small fraction of alpha particles would pass close to it and be deflected sharply by the intense electric field near the nucleus, exactly what Rutherford observed. He described his surprise as like shooting a 15-inch artillery shell at a piece of tissue paper and having it bounce back and hit you. The nuclear model of the atom was established. A tiny, massive, positive nucleus surrounded by a cloud of electrons in an enormous space relative to the size of the nucleus. The emptiness, let me return to the image I started with tonight. The atom is mostly empty space. In Rutherford's nuclear model, the nucleus is approximately 100,000 times smaller than the atom as a whole. In terms of radius, in terms of volume, the nucleus occupies about 1 part in a quadrillion of the atom, 1 part in 1 followed by 15 zeros. Of the atom's volume, the rest is the quantum mechanical electron cloud, which is not empty in a simple sense. The electrons are there, but they are not particles sitting at specific locations. They are probability distributions smeared over the entire volume of the atom, more likely to be found in some places, less likely in others, but fundamentally not localized, not at a specific point, unless measured. So when I say the atom is mostly empty space, I mean it in a specific sense. The nucleus, where virtually all the masses occupies a tiny fraction of the atom's volume, the electron cloud, occupies the rest, but in a quantum mechanical way that is nothing like a simple empty space with a particle floating in it. Why doesn't matter collapse if atoms are mostly empty space? Why can't you put your hand through the table? Why does matter feel solid? The answer is a combination of factors, primarily the Pauli exclusion principle, which we'll get to when we discuss quantum mechanics. Electrons cannot occupy the same quantum state as each other. Two electrons cannot be in the same place at the same time with the same properties. When the electron clouds of two atoms try to overlap, the electrons resist, not because they are physically touching, but because the quantum rules don't allow multiple electrons to occupy the same state. This resistance is the reason matter feels solid. The electron repulsion between overlapping clouds is the force you feel when you press on a table. The table isn't solid. In the sense of being full of matter, it's impenetrably because of quantum mechanical rules that prevent electron clouds from merging. The solidity of the world is a consequence of quantum mechanics, not of matter being full of anything. Light, the speed limit of the universe, light is the first truly extraordinary thing that physics has to say about the world, because light is nothing like what it seems to be when you see the light from a lamp in your room. You are seeing photons, particles of electromagnetic radiation that were emitted by electrons. In the lamp's filament, or lid, or gas discharge tube that traveled through the air at approximately 300,000 kilometers per second and hit the light-sensitive cells of your retina, triggering a cascade of neural signals that your brain interpreted as light 300,000 kilometers per second. That is how fast light travels. In a vacuum, in empty space, let me make that concrete. Light travels from here to the moon in about 1.3 seconds, from here to the Sunday in about 8 minutes and 20 seconds, from here to the nearest star, Alpha Centauri, in about 4.2 years. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, is about 2.5 million light years away. The light you see when you look at Andromeda on a dark night left that galaxy 2.5 million years ago, when our ancestors were early Homo, before our species existed. You are seeing the past. Every time you look at anything, the speed of light is a law, not a coincidence, not a property of the specific photons, but a fundamental constant of the universe. Approximately 299,792,458 meters per second, precisely, known to extraordinary accuracy, and always the same in any vacuum, regardless of who measures it, regardless of how fast. The source of the light is moving. This last point is the revolutionary one. This is what Einstein built his theory of special relativity on in everyday experience. Speeds add. If you're on a train moving at 100 kilometers per hour and you throw a ball in the direction of travel at 50 kilometers per hour, an observer at the side of the track sees the ball moving at 150 kilometers per hour. The speeds add, but light doesn't work like this. If you're on a spacecraft moving at half the speed of light and you shine a beam of light in the direction of travel, an observer at the side of the universe does not see the light moving at 1.5 times the speed of light. They see it moving at exactly the speed of light, the same speed, as if the spacecraft weren't moving at all. This seems impossible. It seems to violate common sense. but it has been verified to extraordinary precision by many different experiments. It is simply how the universe works, and the only way to make it consistent is to conclude that space and time are not absolute, that they are flexible, that they adjust to ensure that everyone measures the same speed for light, regardless of their motion. The consequences of the constant speed of light are extraordinary. They form the basis of Einstein's special theory of relativity, and they include time dilation, moving clocks run slow. A clock on a fast-moving spacecraft ticks more slowly than an identical clock at rest. The faster the motion, the greater the time dilation. At 99% of the speed of light, a clock runs about 7 times slower than a clock at rest. At 99.9999% of the speed of light, it runs about 700 times slower. This is not a hypothetical. It has been measured directly. Atomic clocks flown on aircraft run slightly slow compared to identical clocks on the ground by exactly the amount. Special relativity predicts length contraction. Objects moving at high speed are shorter in the direction of motion than when at rest. Again, the faster the motion, the greater the contraction. Mass-energy equivalence, E equals mc quadrado. Perhaps the most famous equation in science, energy and mass are equivalent, interconvertible, the same thing in different forms. A small amount of mass contains an enormous amount of energy because c, the speed of light, is so large, and c squared is enormous. This is the basis of nuclear energy. The energy released when atoms fission or fuse comes from the conversion of a tiny amount of mass into an enormous amount of energy. Nothing can travel faster than light. This is one of the most profound and most tested results of special relativity. The speed of light is an absolute upper limit on the speed of any massive object. Why? Because as a massive object accelerates, its kinetic energy increases, and by E equals mc squared, energy is equivalent to mass. So the effective mass of the object increases. As it speeds up, and a heavier object needs more force to accelerate it further, the more you push, the more massive it becomes. The harder it is to push. As you approach the speed of light, the effective mass approaches infinity, and the energy needed to accelerate it further also approaches infinity. You can get arbitrarily close to the speed of light, but never reach it. For a massive object, light itself has no mass, which is why it can travel at the speed of light. Only massless particles can travel at c. Everything with mass must travel slower. Parfois, time. The strangest dimension, time, is the concept that physics has found most difficult to pin down, most surprising in its behavior, most resistant to simple description. In everyday experience, time feels like a river flowing in one direction, from past to future, at a uniform rate that everyone shares equally. Physics says all of this is wrong, or at least profoundly incomplete. Time is not absolute. We have already mentioned that moving clocks run slow. Time dilation. The fact that time passes at different rates for different observers, depending on their velocity and their position In a gravitational field, this is not poetic, not metaphorical, not a matter of how time feels. It is a physical fact, measurable, measured, confirmed to extraordinary precision by multiple independent experiments. GPS satellites orbit the Earth at high speed and at significant altitude above the Earth's surface. Their clocks experience two relativistic effects. The speed of the satellite causes time dilation. The satellite's clock runs slightly slow compared to a clock on the ground by about 7 microseconds per day due to the velocity effect, but the satellite is also further from the Earth's mass, and gravity slows time. A clock deeper in a gravitational well runs slower than one in weaker gravity. This is gravitational time dilation. Predicted by general relativity, the satellite's clock runs slightly fast compared to a clock on the ground by about 45 microseconds per day due to the gravity effect. Net result, the satellite clock runs approximately 38 microseconds per day fast relative to the ground. 38 microseconds per day. Sounds like almost nothing, but GPS works by precisely timing signals. A 38 microsecond error per day would cause GPS positions to drift by about 10 kilometers per day. Your phone's maps would stop working. Within days, the GPS system corrects for relativistic effects. The satellite clocks are deliberately set to run slightly slow so that when the relativistic effects speed them up, they end up running at the same rate as ground clocks. Every time you use GPS, you are using the physics of Einstein. The theory of relativity is not an abstract idea. It is engineering running in the satellites above your head. Right now, what is time? The deeper question, what is time actually, is one that physics has made surprising progress on without fully answering. In Newtonian physics, time was absolute, an external river flowing at the same rate for everyone, the backdrop against which everything else happened. In Einsteinian physics, time became part of space-time, a dimension intertwined with the three spatial dimensions, not separate from space, but woven into it. Four-dimensional space-time is the fabric of the universe in general relativity. Mass curves space-time, not just space, but time. A massive object slows time. In its vicinity, time passes more slowly at the bottom of a deep valley than at the top of a mountain because the valley is deeper. In the Earth's gravitational field, this effect is tiny, but measurable. Atomic clocks at different altitudes show this effect directly. The arrow of time. One of the great puzzles of physics is why time has a direction, why it flows from past to future and not from future to past. The fundamental laws of physics are almost completely symmetric. In time, if you filmed a collision between two particles and ran the film backwards, the reversed collision would also obey all the laws of physics, and yet time clearly has a direction. In the macroscopic world, eggs break, they don't unbreak. Heat flows from hot to cold, not from cold to hot. The past is fixed, the future is open. The explanation that most physicists accept is entropy. The second law of thermodynamics systems tend toward disorder over time, not because disorder is preferred by any law, but because there are vastly more disordered states than ordered ones. A random process is far more likely to move toward disorder than toward order, simply because there are more disordered options. The arrow of time is the arrow of entropy, and entropy increases not because the laws of physics demand it, but because of probability. The universe started in an extraordinarily low entropy state, the Big Bang, and has been moving toward higher entropy ever since, and will continue to do so until it reaches maximum entropy in the far future, what some cosmologists call the heat death of the universe. But why did the universe start in such a low entropy state? That is one of the deepest and most unresolved questions in all of physics. Gravity, the weakest force that rules everything, gravity is the strangest of the four fundamental forces, the weakest by an almost incomprehensible margin, and yet the one that governs the structure of the universe at every large scale. The four fundamental forces that we know of are the gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Gravity is by far the weakest. How much weaker compared to electromagnetism? Gravity is weaker by a factor of about 10 to the power of 36. That is a 1 followed by 36 zeros, times weaker. To feel the difference, consider a small magnet on a refrigerator. The magnet is held up against the Earth's gravity by the electromagnetic force of the magnetic interaction between the magnet and the refrigerator door. The electromagnetic force of that small magnet is stronger than the gravitational force of the entire mass of the Earth, pulling the magnet down, and yet gravity rules the universe at large scales because electromagnetism cancels out. Matter is electrically neutral on average. Positive and negative charges balance each other, and the net electromagnetic effect of large amounts of matter is near zero. But gravity doesn't cancel. Mass has only one sign. There is no negative mass to cancel positive mass. The gravitational attraction of every piece of matter simply adds up without cancellation. The bigger the collection of matter, the stronger its gravitational pull. So even though gravity is extraordinarily weak on the scale of particles, on the scale of planets and stars and galaxies, it dominates. It is the architect of the large-scale universe. Newton's description, Isaac Newton, formulated the first mathematical law of gravity in 1687 in his Principia Mathematica, one of the most important scientific works ever written. Newton's law of universal gravitation states that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. If alg sem un sem m tus quadratet, this simple equation explains the orbits of the planets, the tides, the shape of galaxies, the motion of comets, and much more with extraordinary accuracy. But Newton himself was troubled by his own equation. He couldn't explain what gravity was, how it worked, how one mass could attract another mass across empty space without anything connecting them. He called this action at a distance and confessed that he didn't understand it. I feign no hypotheses. He wrote, hypothesis non fingo. I describe what gravity does, not what gravity is. It took 230 years for someone to answer what gravity is. Einstein's description in 1915, Albert Einstein published his general theory of relativity, the most profound revolution in our understanding of gravity. Since Newton, possibly in all of physics, Einstein's answer to Newton's action at a distance problem was radical and beautiful. Gravity is not a force, it is the curvature of space-time, mass and energy curve, space-time, the way a heavy ball curves a stretched rubber sheet, and objects move in response to that curvature, following the straightest possible path through curved space-time, what we call a geodesic, and what appears to us as gravitational attraction is simply objects following the curved geometry of the space-time around them. The Earth orbits the Sunday not because the Sunday is pulling the Earth across empty space with some mysterious invisible force, but because the Sun's mass curves space-time around it, and the Earth follows the curved space-time in what is, from the Earth's perspective, the straightest possible path, which from outside looks like an orbit. This is a complete reconception of what gravity is, not a force, but a geometry, not a pull, but a curvature, not something that travels through space, but a property of space itself, the predictions of general relativity. General relativity makes specific, testable predictions, many of which have been confirmed with extraordinary precision. The bending of light. Light follows geodesics through space-time, just as matter does. And since mass curves space-time, light should be bent when it passes near a massive object. This was first tested during the solar eclipse of 1919, when Arthur Eddington led an expedition to observe the apparent positions of stars near the edge of the Sunday. During the eclipse, when the sun's disk was blocked, the stars appeared in slightly different positions than they would have without the sun there, displaced by the bending of their light as it passed near the Sunday by exactly the amount. General relativity predicted. The measurement made Einstein world famous. Overnight, it was front page news. Around the world, the theory that said space was curved had passed its first major test. Gravitational time dilation. Clocks run slower in stronger gravitational fields. We discussed this in the GPS context. Confirmed many times to extraordinary precision gravitational waves. One of the most dramatic predictions of general relativity is that accelerating masses should produce ripples in space-time gravitational waves, spreading outward at the speed of light. These were predicted by Einstein in 1916, but their direct detection was considered almost impossibly difficult. The waves are extraordinarily weak. By the time they reach Earth, even from catastrophic cosmic events like colliding black holes The stretching and squeezing of space-time at the detector is smaller than 1,000th of the diameter of a proton. The LIGO detectors, built specifically to detect gravitational waves, achieved this for the first time in September 2015, detecting the merger of two black holes about 1.3 billion light years away. The signal lasted about 0.2 seconds. And during those 0.2 seconds, the two black holes released more energy in gravitational waves than the combined luminosity of all the stars in the observable universe. For that brief moment, and what we detected here on Earth was a stretching and squeezing of space itself by less than 1,000th of the diameter of a proton. This is perhaps the most precise measurement ever made by human beings. Quantum mechanics, the rules beneath reality, quantum mechanics, is the most successful theory in the history of science, measured by the precision of its predictions and the range of phenomena it correctly describes. It is also perhaps the most disturbing, the most counterintuitive, the most philosophically challenging theory ever developed. Richard Feynman, one of the greatest physicists of the 20th century, and the man who understood quantum mechanics as well as anyone who ever lived, said, if you think you understand quantum mechanics, you don't understand quantum mechanics. This is not false modesty. It is a genuine observation about the nature of the theory. Quantum mechanics is a recipe for calculating the probabilities of outcomes of measurements. It is extraordinarily precise. In those calculations, it works every time to extraordinary accuracy. But what it means, what it is actually saying about the nature of reality, is genuinely unclear and has been debated by the greatest physicists of the past century without resolution. The origins of quantum mechanics emerged in the early 20th century from a series of experimental observations that classical physics could not explain. Blackbody radiation, the pattern of radiation emitted by a hot object, could not be explained by classical electromagnetic theory. The theory predicted that hot objects should emit infinite energy at high frequencies, a result known as the ultraviolet catastrophe, because it was catastrophically wrong. Max Planck in 1900 proposed a solution. He suggested that energy could only be emitted or absorbed in discrete packets, quanta, multiples of a fundamental unit, now called Planck's constant. This was a desperate measure. Planck himself didn't believe it represented physical reality. He thought it was a mathematical trick that happened to work, but it did represent reality, as Einstein showed in 1905, when he used Planck's idea to explain the photoelectric effect, the observation that light can knock electrons out of metal only above a certain frequency, regardless of intensity. This implied that light came in discrete packets, photons, each with an energy proportional to its frequency. For this explanation of the photoelectric effect, Einstein won the Nobel Prize, not for relativity, for quantum mechanics. The full theory was developed through the 1920s by Heisenberg, Schrödinger, Bohr, Born, Dirac, Pauli, and others in one of the most concentrated, brilliant bursts of theoretical physics in the history of science. The wave function at the heart of quantum mechanics is the wave function, a mathematical object that describes the quantum state of a particle or a system of particles. The wave function contains all the information that can be known about the system, but it does not give definite values for observable properties like position or momentum. It gives probabilities, the probability of finding the particle in a particular position, the probability of measuring a particular momentum. Before you measure, the particle doesn't have a definite position. It has a probability distribution of position smeared out over a region of space in the wave function. When you measure, the wave function collapses to a definite value. The particle is found at a specific location and the probability distribution disappears. What does this mean? Does the particle really not have a definite position before measurement? Or does it have one, but we just don't know what it is? The answer, according to the most common interpretation of quantum mechanics, the Copenhagen interpretation, is that the particle genuinely does not have a definite position before measurement. The measurement doesn't reveal a pre-existing position. It creates the position. This is deeply strange, and not everyone accepts it. There are other interpretations of what quantum mechanics means that try to restore a more classical sense of reality, but all of them come with their own deep strangeness. Wave-particle duality, the thing that should be impossible. One of the clearest demonstrations of quantum strangeness is the double-slit experiment Consider a barrier, with two narrow slits and a screen behind it to detect what passes through. If you fire a particle, bullets, for example, at the barrier, some go through one slit, some go through the other, and they hit the screen in a pattern of two bands directly behind each slit, exactly what you'd expect from classical particles. If you send waves, light waves, for example, through the two slits, the waves spread out from each slit and interfere where they meet. Constructive interference, where two peaks meet, makes a bright band. Destructive interference, where a peak meets a trough, makes a dark band. An alternating pattern of light and dark bands called an interference pattern. Now fire a beam of electrons through the two slits. What pattern do you get on the screen? You get an interference pattern, not two bands. An interference pattern like a wave, but the electrons are particles, not waves. How can particles create an interference pattern? The answer is because electrons are waves and particle, both simultaneously. In quantum mechanics, every particle has a wave function that describes its quantum state, and that wave function behaves like a wave. It spreads out and interferes with itself, passing through both slits simultaneously, creating the interference pattern. On the other side, now here is where it gets more deeply strange. If you fire electrons one at a time and record where each one lands, Each individual electron hits the screen at a single specific point, like a particle. But over time, as you fire more and more electrons, one at a time, the accumulated pattern of where they hit is the interference pattern. Each electron somehow interferes with itself, going through both slits simultaneously and landing at the screen as a particle in a location determined by the interference of its own wave function. And if you try to find out which slit the electron went through by placing a detector at the slits to observe the electron, the interference pattern disappears. The electron goes through only one slit, and you get the two-band pattern of classical particles. The act of observing which slit the electron went through destroys the interference. The mere presence of the detector, even if you don't actually look at the result, changes what happens. This is what physicists mean when they say observation affects the system. It is not about consciousness or human observers. It is about physical interaction between the detector and the particle. Any physical interaction that could in principle determine which slit the particle went through destroys the interference. The electron somehow knows whether it is being watched and behaves differently. If it is, this is wave-particle duality, the experimental fact that quantum objects display wave-like behavior and particle-like behavior depending on how you interact with them, but never both simultaneously, entanglement, connected across any distance. Perhaps the most astonishing of all quantum effects is entanglement. When two particles interact, in certain ways, they can become entangled. Their quantum states are linked in a way that persists, even when the particles are separated by great distances. When you measure a property of one entangled particle and get a specific result, the other particle instantaneously takes on a correlated state, no matter how far apart they are. For example, two particles can be produced in a state where their spins must be opposite, one up, one down, but before measurement, neither has a definite spin. Each has a probability of being found up or down. When you measure the spin of one particle and find its spin up, the other particle is instantaneously spin down wherever it is, even if it's on the other side of the universe. This seems to imply some kind of instantaneous communication between the particles, faster than light, which special relativity appears to forbid. Albert Einstein hated this idea. He called it spooky action at a distance and was convinced that it couldn't be right, that quantum mechanics must be incomplete, that there must be hidden variables, information carried by the particles that determines the outcome before measurement, so that no actual instantaneous communication was needed. In 1964, the physicist John Bell derived a mathematical inequality, now called Bell's inequality, that could distinguish between the quantum mechanical prediction and any hidden variables theory that preserved a classical view of reality. If hidden variables existed, the correlations between the measured properties of entangled particles should satisfy Bell's inequality. If quantum mechanics was right, they should violate it. The experiments, beginning in the 1970s and continuing with increasing precision to the present day, universally, unambiguously violate Bell's inequality in exactly the way quantum mechanics predicts. This means hidden variables of the simple kind cannot explain the correlations. The particles do not carry pre-existing information. That determines the measurement outcomes. The outcomes are genuinely random until measured, and yet the correlations are real and immediate, regardless of distance. Does entanglement allow faster than light communication? No. And this is the subtle point that saves physics from contradicting itself. When you measure one particle and find its spin up, you cannot control what outcome you get. The outcome is random. You cannot send a prearranged message by controlling the spin of your particle because you don't control it. The result is random. The correlation only becomes visible when you compare the results of measurements on both particles after the fact through a classical channel which cannot travel faster than light. So entanglement is a genuine non-local correlation between quantum systems that cannot be explained classically, but that also cannot be used to transmit information faster than light. The universe is strange, but consistent. The uncertainty principle, the fundamental limit of knowledge. In 1927, Werner Heisenberg formulated one of the most profound and most misunderstood results in physics, the uncertainty principle. The uncertainty principle states that there is a fundamental limit to how precisely certain pairs of physical properties can be known simultaneously. The most famous pair is position and momentum. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. This is not a limitation of our instrument, not a reflection of our ignorance. It is a fundamental feature of reality. This is not a limitation of our instrument, not a reflection of our ignorance. It is a fundamental feature of reality. The uncertainty principle arises from wave-particle duality. A particle with a very well-defined position is localized in space, like a spike, a narrow wave packet. But a narrow spike is made up of many different wavelengths. And in quantum mechanics, momentum is related to wavelength. A narrow wave packet contains a range of wavelengths, and therefore a range of momenta. Conversely, a particle with a well-defined momentum has a well-defined wavelength, which means its wave function extends over a large region of space, and its position is correspondingly uncertain. The uncertainty principle implies something remarkable. A particle can never be perfectly at rest, even at absolute zero temperature. Even with no thermal energy, it still has a minimum uncertainty. In its position and momentum, this minimum energy is called the zero-point energy, and it has real physical consequences. The Casimir effect: two parallel metal plates placed very close together in a vacuum experience a tiny attractive force. The Casimir effect. Why? Because the vacuum is not truly empty. Quantum mechanics says the vacuum is full of fluctuating quantum fields, virtual particles, appearing and disappearing faster than they can be detected, borrowing energy from the uncertainty principle, the energy-time uncertainty, a variant of the position momentum one between the plates. Only certain wavelengths of virtual photons can exist. Those that fit within the gap outside the plates, all wavelengths exist. The result is a slight imbalance, more virtual photons outside than between, pushing the plates together. The Casimir effect has been measured. It is real. The vacuum is not empty. It is seething with quantum fluctuations that have real physical effects. Dark matter, the invisible majority. In the 1970s, an astronomer named Vera Rubin was studying the rotation of spiral galaxies. She expected to find that the outer parts of galaxies rotate more slowly than the inner parts, just as the outer planets of the solar system move more slowly than the inner ones, because the gravitational pull of the central mass decreases with distance. She found instead that the outer regions of galaxies rotate at roughly the same speed as the inner regions. The rotation curve was flat, not falling off with distance. As expected, this implied that there was more mass in the outer regions of galaxies than could be accounted for by the visible stars and gas. The unseen mass was needed to produce the observed rotation. Subsequent observations confirmed this in many different ways. Galaxy clusters move as if they contain far more mass than the visible matter. The bending of light by galaxy clusters, gravitational lensing, shows the same. More mass than can be seen. This unseen mass is called dark matter, and it makes up approximately 27% of the total mass energy of the universe. The visible matter, the stars and gas and dust and planets and everything we can see, makes up only about 5%. Dark matter is not dark in the sense of being obscured or shadowed. It doesn't interact with electromagnetic radiation at all. It doesn't absorb or emit or scatter light or any other form of electromagnetic radiation, which is why it is invisible. What is dark matter? We don't know. This is one of the most significant admission. In contemporary physics, 27% of the universe is made of something that we cannot directly observe, cannot create or detect in any laboratory, and whose nature is completely unknown. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that have mass but interact only via the weak nuclear force and gravity, not electromagnetism, making them invisible to light. Axion, very light hypothetical particles, originally proposed to solve a different problem. In particle physics, the strong CP problem that could also be dark matter, sterile neutrinos, hypothetical heavy neutrinos that don't interact via any force except gravity. None of these has been directly detected, despite extensive searches in underground laboratories At particle accelerators and in astronomical observations, dark matter is real. Its gravitational effects are unambiguous, but what it is remains completely unknown. Dark energy, the force pulling everything apart. In 1998, two independent research teams were measuring the distances and velocities of type Ia supernovae, explosions of a specific type that have a known intrinsic brightness, making them useful as standard candles. For measuring cosmic distances, they expected to find that the expansion of the universe was slowing down due to the gravitational attraction of all the matter in the universe, pulling everything back together. They found the opposite. The expansion is accelerating. The universe is not slowing down. It is speeding up. The distant supernovae were further away than expected for a decelerating universe. This was so unexpected that the teams double and triple checked their results before publishing, but the result was right and has been confirmed many times since by many independent methods. The expansion of the universe is accelerating. What is causing the acceleration? Something is counteracting the gravitational pull of matter, some form of energy associated with empty space. That has a repulsive antigravitational effect. This unknown energy is called dark energy. It makes up approximately 68% of the total energy of the universe. So the inventory of everything in the universe is 5% ordinary matter, the stuff you and I are made of, the stuff we can see, 27% dark matter, unknown, invisible, detected only gravitationally, 68% dark energy, unknown, associated with space itself, causing the accelerating expansion. 95% of the universe is unknown, made of things we cannot directly observe, whose natures are completely mysterious. The visible universe, the stars and galaxies, and the planets and nebulae and quasars, and all the extraordinary, beautiful things that astronomers study is only 5% of what's there. This is a remarkable and humbling statement about the state of human knowledge. We have an extraordinarily precise and successful description of 5% of the universe, and the other 95% is labeled with the honest word dark. We can see the effects. We cannot explain the cause. Black holes, where physics breaks down, black holes are perhaps the most dramatic of all the predictions of general relativity, and the objects that most clearly show where our current physics reaches its limits. A black hole forms when a large mass is concentrated into a sufficiently small volume so that the escape velocity from the surface exceeds the speed of light. Escape velocity is the speed you need to escape from the gravitational field of an object without any further propulsion. The escape velocity from Earth is about 11 kilometers per second, about 40,000 kilometers per hour. For a black hole, the escape velocity exceeds c, the speed of light. And since nothing can travel faster than light, nothing can escape. Not matter, not radiation, not light itself. everything that passes the event horizon, the boundary of the black hole, is gone from the outside universe forever. The event horizon is not a physical surface. There is nothing special about the location of the event horizon from the inside, from the perspective of someone falling into a black hole. They would cross the event horizon without noticing, without any local sign, that they had crossed a boundary of no return. But from outside, from the perspective of an observer, far from the black hole, the infalling person would appear to slow down as they approached the event horizon, their time gravitationally dilated. By the intense gravitational field, their light redshifted to lower and lower energies until they appeared to freeze at the event horizon and fade away, asymptotically approaching, but never quite reaching the horizon in the outside observer's time, the singularity inside the event horizon. According to general relativity, everything is drawn inexorably toward the center, toward the singularity, a point of infinite density, where the curvature of space-time becomes infinite, and the equations of general relativity simply break down, give meaningless answers, infinities, where finite numbers should be. The singularity is not a place in the usual sense. It is a point where our description of reality fails, where the theory that told us about the black hole in the first place stops working. Most physicists believe that the singularity is not real, that it is a sign of the incompleteness of general relativity, that a complete theory of quantum gravity would replace the singularity with something finite and physically meaningful, but we don't have that theory yet. The Schwarzschild radius, the size of the event horizon of a black hole, depends only on its mass. The formula is simple. R égale 2gm divisé par c carré, where g is Newton's constant, m is the mass, and c is the speed of light for the Earth. If you compressed all its mass into a sphere, the radius would be about 9 millimeters. A marble containing the entire Earth would become a black hole. For the Sunday, the Schwarzschild radius is about 3 kilometers. The entire Sunday compressed to 3 kilometers for a black hole, 10 times the mass of the Sunday, about 30 kilometers. These are stellar mass black holes that form when massive stars collapse at the end of their lives. For the supermassive black hole at the center of the Milky Way, Sagittarius A, with a mass of about 4 million times the Sunday, the Schwarzschild radius is about 12 million kilometers, about a sixth of the Earth-Sun distance. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, produced the first image of a black hole's shadow, the supermassive black hole, at the center of galaxy M87, 6.5 billion times the mass of the Sunday. A bright ring of hot gas around the dark shadow, the darkness of the event horizon against the light of the surrounding accretion disk. The image was a profound moment, an object that had been a theoretical prediction for over a century. directly imaged for the first time the Big Bang, the beginning of everything. The universe had a beginning. This is one of the most profound and most tested results in all of cosmology. The evidence is multiple, independent, and converging on the same conclusion: the expansion. The universe is expanding, observed by Edwin Hubble. In 1929, galaxies are moving away from us, and the more distant they are, the faster they are receding. Run the expansion backwards. And everything was once closer together, all the matter and energy of the observable universe in a smaller and smaller space. As you go back in time, the cosmic microwave background. In 1965, Arno Penzias and Robert Wilson accidentally discovered a faint microwave radiation coming equally from all directions in the sky. This is the cosmic microwave background. CMB, the afterglow of the early universe. When the universe was about 380,000 years old, it cooled enough for atoms to form for the first time. Before that, the universe was a hot plasma, opaque to radiation. When atoms formed, the radiation that had been trapped in the plasma was suddenly free to travel, and it has been traveling ever since, stretched by the expansion of the universe. From visible light, the microwaves reaching us now from every direction are relic of the early universe. The abundances of light elements the Big Bang predicts, specific abundances of hydrogen, helium, lithium, produced in the first few minutes after the Big Bang, when the universe was hot enough for nuclear reactions, but not for long. The observed abundances of these elements match the predictions of Big Bang nucleosynthesis to extraordinary precision. What came before the Big Bang? This is the question that physics currently cannot answer. General relativity applied to the early universe predicts a singularity at the beginning, a moment when the density and temperature of the universe were infinite, before which time itself had no meaning, like the singularity inside the black hole. The Big Bang singularity is most likely a sign that general relativity is incomplete, that a full theory of quantum gravity would give a better description of the very beginning without the singularity. Various proposals exist for what that description might look like. Stephen Hawking and James Hartle proposed a no-boundary proposal, in which the universe has no beginning in the usual sense, but the concept of before has no meaning before a certain point, because time becomes a spatial dimension near the beginning. Roger Penrose has proposed conformal cyclic cosmology, in which the universe goes through an infinite sequence of cycles, each Big Bang being the end of a previous cycle. Lee Smolin has proposed cosmological natural selection, in which universes give birth to new universes inside black holes with slightly different physical constants. None of these is the established answer. All of them are speculative. The question of what, if anything, came before the Big Bang, or what caused the Big Bang, remains genuinely open. One of the deepest and most fundamental questions in all of physics the fine-tuned universe, why the constants are what they are. The universe has constants, numbers that appear in the laws of physics that determine the character of the universe. The strength of gravity, the speed of light, the mass of the electron, the charge of the electron, the strength of the strong nuclear force, the strength of the weak nuclear force, the cosmological constant, the value of dark energy. These constants have specific values that we measure but cannot derive from any deeper theory. They are inputs to the equations, not outputs, and they are extraordinarily finely tuned for the existence of complexity, of stars, of planets, of chemistry, of life. If the strength of gravity were slightly different, stars wouldn't form or wouldn't burn for long enough for planets to develop and life to emerge. If the strong nuclear force were slightly weaker, atomic nuclei would be unstable, and atoms as we know them wouldn't exist. If it was slightly stronger, all hydrogen would fuse in the early universe, and there would be no hydrogen left for stars or water. If the cosmological constant were much larger, the universe would have expanded too fast for matter to clump into galaxies, stars, planets. If it were much more negative, the universe would have recollapsed almost immediately, long before any complexity could develop. The value we observe is extraordinarily small compared to what quantum field theory naively predicts it should be. This discrepancy between the predicted and observed value of the cosmological constant is sometimes called the worst prediction in physics, the worst in the sense of the largest discrepancy between theory and observation in the history of science, about 120 orders of magnitude of what does this fine-tuning mean. Physicists and philosophers have debated this for decades without consensus. One view is that the fine-tuning suggests design, that the constants were chosen to allow complexity and life by some form of intelligence or intentionality. Physics as a science cannot adjudicate this question. It is a philosophical question or a theological one, not a scientific one. In the strict sense, another view is the multiverse. If there are many universes with different physical constants, each drawn from some distribution, then we should not be surprised to find ourselves in a universe with constants that permit our existence, because we can only observe a universe that permits our existence. This is the anthropic principle. A third view is that a future, deeper theory of physics will explain why the constants have the values they do from some more fundamental principle that we don't yet know. None of these views is established as definitely correct. The fine-tuning of the universe remains one of the deepest and most genuinely open questions in science. The philosophy of physics, what these discoveries mean for how we see the world. Let me step back from the specific physics and sit with what it means. Physics has discovered over the past century that the world is radically different from what common sense or everyday experience would lead us to expect matter is mostly empty space, time is not absolute, space curves, particles don't have definite positions until measured. Measurement changes. What is measured, entanglement connect particles across any distance. 95% of the universe is unknown, even in principle. The question of what came before, the beginning, may not have an answer. Within physics, as currently formulated, this is remarkable, not because it is frightening, but because it is humbling and because it points to something important about the nature of knowledge itself. The universe does not owe us simplicity or intuitiveness or comfort. It does not need to be comprehensible by human minds, evolved to navigate a medium-sized world at medium speeds with medium-sized things, and yet it is at least partially comprehensible. We can understand quantum mechanics even if we can't visualize it. We can solve the equations of general relativity even if we can't draw a picture of four-dimensional curved space-time. We can predict the positions of planets to extraordinary precision and detect gravitational waves from colliding black holes a billion light years away. The human mind is not large enough to contain the universe, but it is large enough to ask the right questions and to build the tools, mathematical and experimental, to find the answers. That is one of the most extraordinary things about being human. We are made of atoms that are mostly empty space in a universe that is 95% unknown, on a planet that circles a star that is one of 200 billion in a galaxy that is one of 2 trillion in the observable universe. And somehow we figured this out. We measured the expansion of the universe. We detected particles born in the collisions at the dawn of time. We imaged a black hole at the center of another galaxy. We traced the history of the universe back to fractions of a second. After its beginning, this is not nothing. This is one of the most extraordinary things that has ever happened in the history of the universe. As far as we know, a part of the universe looking back at itself and understanding what it is, the closing, the universe wondering about itself. There is a phrase that I love, attributed to Carl Sagan, though the idea goes back further. We are the universe, observing itself. We are made of atoms, forged in the cores of ancient stars that exploded and scattered their contents through the galaxy, which eventually coalesced into our solar system, our planet, our oceans, our chemistry, our biology, ourselves. The carbon in your body was forged in the core of a star that lived and died before the solar system existed. The iron in your blood was forged in the explosion of a supernova. The calcium in your bones, the oxygen you breathe, the nitrogen in your DNA, all of it made in stars, scattered by explosions, gathered by gravity into you. You are made of the universe, and the universe used you to look at itself. Physics is, in its most fundamental sense, the universe's way of understanding what it is, using the minds it assembled from its own matter to reflect on its own nature, and what it has found so far is strange and beautiful and deeply incomplete. There are more questions now than there were a century ago, because every answer reveals deeper questions. That is how it works. That is how it has always worked. Let your breathing slow. Let the images settle. The atom, mostly empty space, but somehow solid. The photon traveling through curved space-time for 8 minutes. From the Sunday to your eye, the electron in its quantum cloud, nowhere specific, until you look the black hole at the center of a galaxy, curving space-time so severely that nothing can escape. The universe expanding, accelerating, driven by something we cannot name, the beginning 13.8 billion years ago, before which time had no meaning and which we cannot see beyond. Yet the universe has been doing this for 13.8 billion years. It was not waiting for us to understand it. It was just being itself, following the rules that it follows perfectly every time. And we are the part of it that wonders why. Rest now. The physics doesn't stop while you sleep. The atoms in your body keep vibrating. The electrons keep dancing in their quantum clouds. The space-time around your planet keeps curving as the Earth moves through the universe. The universe will still be here when you wake up, exactly as strange, exactly as beautiful, exactly as incomprehensible, and exactly as real as it is right now. Close your eyes. Before we continue tonight, I want you to do something again. Look at your hand, the same hand we started with, but now you know more about it. 7 octillion atoms, each one mostly empty space, each one following rules that have not changed. Since the first moments of the universe, you've been lying here, listening, while the atoms in your body did what they always do, without asking your permission, without needing your attention. Electrons dancing in quantum clouds, protons and neutrons, held together by the strong force inside nuclei so small that if you enlarged one atom to the size of a football stadium, the nucleus would be a grain of sand. At the center, you've learned that the solidity of your hand is not about matter being full, but about quantum rules that prevent electron clouds from merging. You've learned that the light in your room travels at exactly 299,792,458 meters per second, always, regardless of anything, and that this single fact forces time itself to be flexible. You've learned that gravity is not a force, but a curvature of space-time itself, and that we confirmed this by detecting ripples in space-time from 2 black holes colliding 1 billion light years away. Tonight, we go deeper. We're going to look at the places where our understanding is most uncertain, most beautiful, most strange. We're going to look at what quantum field theory says about the nature of particles. We're going to explore the interpretations of quantum mechanics, the debate that has occupied the greatest minds for a century. Without resolution, we're going to look at the attempt to unify everything. String theory loop quantum gravity, the search for the theory of everything. And we're gonna end where we always end, with you and what any of this means for something as small as a single human life. So breathe slowly, let the images from the first part settle, and let's go back in. Quantum field theory. The world is not made of particles. Here is something that may surprise you. Given everything we've discussed, the world is not made of particles. Not really. Not at the deepest level that physics currently understands. Particles are useful fictions, convenient descriptions that work extraordinarily well at certain scale and in certain contexts, but the deeper description, the description that quantum mechanics and special relativity forced physicists toward starting in the 1920s and fully developed by the 1940s and 50s, is this: the world is made of fields, not particles, fields. What is a field? A field in physics is something that has a value at every point in space and at every moment in time. The simplest example is temperature. Temperature is a field. At every point in a room, there is a temperature. Some places warmer, some places cooler, but every point has a value. A more physical example is the gravitational field. At every point in space, there is a gravitational field pointing toward the nearest massive objects with a strength that depends on how far away those objects are and how massive they are. Quantum field theory says that the universe is filled with fields, one for each type of fundamental particle. An electron field that fills all of space, a photon field that fills all of space, a quark field, several of them, for each type of quark that fills all of space, a Higgs field that fills all of space. These fields permeate everything. They are everywhere. In the room you're in right now, in the space between galaxies, in the interior of the Sunday, everywhere, always, particles are excitations of these fields. When a field is disturbed, when something gives it enough energy in a small enough region, it creates a particle, a localized, quantized ripple in the field. An electron is not a tiny ball of negative charge sitting at a specific location. It is on excitation, a disturbance, a ripple in the electron field that permeates all of space. A photon is a ripple in the electromagnetic field. A quark is a ripple in a quark field. The Higgs boson that was discovered at the Large Hadron Collider in 2012 is a ripple in the Higgs field. This changes how we think about empty space. Empty space is not nothing. It is a collection of fields, all in their lowest energy state, their ground state, when nothing is disturbing them. Empty space is full of fields, quiet but present everywhere. The vacuum, what we call the vacuum, the most empty state possible, is the state where all the fields are in their ground state. No excitation, no particles, but still the fields themselves filling everything. And even this ground state is not truly quiet. Quantum mechanics and the uncertainty principle guarantee that even in the ground state, there are fluctuations, random, unavoidable fluctuation of the fields these vacuum fluctuations are real. They have measurable effects. The Casimir effect that we discussed in the first part is a direct consequence of vacuum fluctuations of the electromagnetic field. Another consequence is the Lamb shift, a tiny shift in the energy levels of hydrogen atoms, first measured by Willis Lamb in 1947. That cannot be explained by Dirac's equation alone, but is precisely predicted by quantum electrodynamics. The quantum field theory of electromagnetism. The fluctuations of the vacuum reach into the atom and shift its energy levels by a tiny, precisely calculable amount. This is extraordinary. The emptiness of space is not empty. It reaches into atoms and changes their properties in ways we can calculate and measure and confirm. The Standard Model, the most successful theory in the history of science, quantum field theory, applied to the fundamental particles and forces, except gravity, is called the Standard Model of particle physics. It is, by any measure, the most successfully tested theory in the history of science. Its predictions for certain quantities have been confirmed to better than one part in 10 billion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. The Standard Model describes 12 fundamental particles of matter, 6 quarks, named up, down, charm, strange, top, bottom, si slept done, the electron, the muon, tau, and 3 neutrinos, 1 for each. It describes 4 fundamental forces, except gravity, electromagnetism, carried by the photon, the strong nuclear force carried by gluons, the weak nuclear force carried by W and Z bosons, and it describes the Higgs field and the Higgs boson, which gives mass to the fundamental particles that have mass. Every particle you've ever heard of, proton, neutron, atom, every piece of matter you've ever touched is made of combinations of these 12 particles interacting through these forces. The quarks are held together inside protons and neutrons by the strong force carried by gluons in a way that is itself extraordinarily strange. The strong force does not get weaker as quarks move apart, unlike gravity and electromagnetism, which both weaken with distance. The strong force stays constant. As quarks separate, this means you can never pull a quark out of a proton or neutron on its own. If you try, the energy needed to pull the quarks apart is enough to create new quarks and antiquarks. From the vacuum, the strong force field and those new quarks immediately combine with the ones you're trying to separate to form new particles, rather than letting you pull apart a quark into open space. Quarks are always confined, always inside composite particles called hadrons. This is called confinement, and explaining it mathematically from the equations of the strong force remains one of the unsolved mathematical problems of the 21st century, one of the Clay Mathematics Institute Millennium Prize problems, worth $1 million, to whoever solves it, the neutrinos, perhaps the strangest of the standard model particles, are the neutrinos. Neutrinos have almost no mass. For a long time, we thought they had no mass at all, but we now know they have a tiny but non-zero mass. One of the few places where the standard model, as originally formulated, was wrong. Neutrinos interact only via the weak nuclear force and gravity. They do not interact electromagnetically, which means they pass through matter almost completely undisturbed. Right now, about 100 billion neutrinos from the Sunday are passing through every square centimeter of your body every second. You cannot feel them. They do not notice you. They pass through the entire Earth as if it weren't there. Most of them, the number of neutrinos in the universe is almost incomprehensible, about 10 to the power of 89. A followed by 89 zeros, they outnumber the atoms in the observable universe by a factor of roughly 1 billion. They are the most numerous massive particle in the universe, and they pass through everything, like the universe barely registers them, the Higgs field. In 2012, physicists at CERN, the European Organization for Nuclear Research, announced the discovery of a new particle with properties consistent with the Higgs boson predicted by the standard model. In 1964 by Peter Higgs and others, the Higgs boson is the excitation of the Higgs field, which permeates all of space and which gives mass to the fundamental particles that have mass. Why do particles have mass? In the standard model, particles have mass because they interact with the Higgs field. The more strongly a particle interacts with the Higgs field, the more massive it is. Particles that don't interact with the Higgs field, like photons, are massless. The Higgs field has a non-zero value everywhere in space, even in the vacuum. This is called the vacuum expectation value of the Higgs field. It's as if the ground state of the universe is filled with Higgs field, and particles moving through it interact with it. And that interaction manifests as mass. Finding the Higgs boson required the largest, most complex, most expensive scientific instrument ever built, the Large Hadron Collider at CERN, a circular tunnel 27 kilometers in circumference under the Swiss-French border, in which protons are accelerated to 99.9999991% of the speed of light and collided millions of times per second, creating showers of particles that are detected by instruments the size of apartment buildings. And in the debris of those collisions, they found the Higgs boson, a particle that exists for about 1/70th of a second before decaying into other particles, but whose signature in the detectors matched the prediction of the standard model made 48 years earlier. That is physics working. As physics works, prediction, experiment, confirmation or refutation, and the willingness to follow the math wherever it leads, even if it takes 48 years and a 2,7 kilometer tunnel to check the interpretations of quantum mechanics What does it actually mean? Quantum mechanics works. This is not in dispute. Its predictions for the outcomes of measurements are reconfirmed again and again to extraordinary precision. But what quantum mechanics means, what it is actually saying about the nature of reality, is genuinely unclear and has been the subject of passionate debate among the greatest physicists. Since the theory was developed, this is unusual. In most areas of science, the debate is about which theory is right. Here, the debate is about what the correct theory means, the measurement problem. At the heart of the debate is the measurement problem. In quantum mechanics, a particle before measurement is described by a wave function, a superposition of many possible states. An electron, before its position is measured, is not at a specific location. It has a probability distribution of locations. It is, in some sense, in many places at once. When a measurement is made, the wave function collapses. The probability distribution becomes a single definite value. The electron is found at a specific location, but what causes the collapse? What counts as a measurement? Does consciousness play a role or any physical interaction? Is the collapse real or apparent? Different interpretations give different answers to these questions, all of them consistent with the experimental predictions of quantum mechanics, all of them making the same predictions for any experiment you could do, and yet describing radically different underlying realities. The Copenhagen interpretation, the oldest and for a long time most widely accepted interpretation, is the Copenhagen interpretation associated with Niels Bohr and Werner Heisenberg. Copenhagen says there is no deeper reality behind the wave function. The wave function is the complete description of the quantum system. Questions about what the system is doing between measurements are meaningless. We can only speak of the outcomes of measurements, not of underlying reality. There is no quantum world. Bohr is reported to have said, there is only an abstract quantum description. This is an extremely pragmatic position. It says, the physics works, use it, and stop asking what it means. Einstein hated this. He believed there must be an underlying reality, that quantum mechanics was failing to describe completely. God does not play dice. He said, meaning the randomness of quantum mechanics must be apparent, not fundamental. Bohr replied, stop telling God what to do. The debate between Einstein and Bohr is one of the great intellectual confrontation of the 20th century. It played out over decades at conferences, in letters, in papers. Einstein never accepted the Copenhagen interpretation. He died, still convinced that quantum mechanics was incomplete. The Bell experiments, which we discussed in the first part, showed that the hidden variables that Einstein hoped would complete quantum mechanics could not be of the simple local kind he imagined, but they didn't resolve the deeper question of what quantum mechanics means, the many worlds interpretation. In 1957, a Princeton graduate student named Hugh Everett proposed a radical alternative To Copenhagen, Everett suggested that the wave function never collapses. It keeps evolving according to the Schrödinger equation, always, without exception. When a measurement is made, the universe branches into multiple worlds, one for each possible outcome, all of them equally real. When you measure the spin of an electron and find its spin up, you haven't caused the wave function to collapse. The universe has branched into two universes, one in which you found spin up and one in which you found spin down, both equally real. You exist in both different versions of you, getting different results, unaware of each other, separated into parallel branches of the universal wave function. The many worlds interpretation takes quantum mechanics. With absolute seriousness, it says the Schrödinger equation is literally true, always, and what follows is that the universe is vastly larger than we think, constantly branching into countless parallel realities. This sounds like science fiction, but it is taken seriously by many professional physicists, including some at the very top of the field. The appeal is that it requires no additional postulates, no mysterious collapse, no special role for measurement, just the wave function evolving as the Schrödinger equation says it should. The cost is an extraordinary proliferation of unobservable parallel worlds, which some physicists find too high a price. For the elegance, the pilot wave interpretation, David Bohm in 1952 proposed a different approach, inspired partly by Einstein's hope for a more complete theory. In Bohm's interpretation, particles do have definite positions. All the time, the wave function is real, but it acts as a pilot wave, guiding the particle through space. The randomness of quantum mechanics comes from our ignorance of the exact initial positions of particles, not from fundamental indeterminism. This interpretation restores a classical sense of particles with positions and is therefore more intuitively satisfying. To some physicists, the cost is that the pilot wave must be non-local. It must instantaneously respond to changes anywhere in the universe, including changes made to entangled particles far away. This non-locality is exactly what the Bell experiments show is necessary. Relational quantum mechanics, a more recent interpretation proposed by Carlo Rovelli, says that quantum states are not absolute, but relational. A particle's quantum state is not defined in itself, but only relative to other systems. In this interpretation, there is no single observer-independent description of reality. Different observers have different and equally valid descriptions of the same quantum system. There is no paradox here, says Rovelli, only a failure to realize that quantum mechanics is fundamentally about relations between systems, not about systems in themselves. Which interpretation is correct? The honest answer is that we don't know. All of the major interpretations make exactly the same experimental predictions. They are, as far as we can tell, empirically indistinguishable. The choice between them is a choice about what kind of reality we find most compelling, what kinds of entities we're willing to include in our ontology, our account of what exists. This is philosophy, not physics, in the strict sense, and physicists have different views about how much time should be devoted to it. Some think it deeply important. Others think we should just compute and shut up. What is remarkable is that after a century of the most intense intellectual scrutiny by the greatest minds that physics has produced, the question of what quantum mechanics means remains genuinely open. The universe is not obliged to make sense to us, but it does allow us to predict what will happen when we measure it, and sometimes that has to be enough. Quantum gravity, the problem that changes everything, quantum mechanics, and general relativity are both extraordinarily successful. Theories, quantum mechanics, describes the behavior of particles in fields at the smallest scales. Its predictions are confirmed to extraordinary precision. General relativity describes the behavior of space and time and gravity at the largest scales. Its predictions are also confirmed to extraordinary precision. They disagree. Fundamentally, general relativity is a theory of smooth spacetime, a continuous four-dimensional fabric that curves in response to mass and energy, and whose geometry determines the motion of everything in it. Quantum mechanics says the world is granular, discrete, probabilistic, fields that fluctuate, particles that don't have definite properties until measured. When you try to apply quantum mechanics, the gravity, to the gravitational field itself, the mathematics breaks down. You get infinities, meaningless divergences that cannot be removed by the technique that work for the other forces. This is a problem because there must be a quantum theory of gravity. Under extreme conditions, both theories apply inside a black hole, where the density becomes so large that quantum effects cannot be ignored. At the Big Bang, where the entire universe was compressed into a volume smaller than a particle. At those scales, both quantum mechanics and gravity must be relevant, and we have no theory that describes both correctly. The two great theories of 20th century physics are mathematically incompatible. One of them must be modified, or both, by a deeper theory that includes both. As limiting cases, the way Newton's gravity is a limiting case of general relativity for weak fields and low velocities. The search for this theory, the theory of quantum gravity, is the central unsolved problem of theoretical physics today. String theory, the most developed and most studied candidate for a theory of quantum gravity, is string theory. The basic idea is radical. The fundamental entities of the universe are not point particle, zero-dimensional, with no size, but one-dimensional strings, tiny vibrating loops, strands of energy. The different particles we observe Electrons, quarks, photons are not different types of things. They are the same strings, vibrating in different ways. The way a guitar string can vibrate at different frequencies and produce different notes. A string vibrating in one mode is an electron, in another a quark, in another a photon. Among the vibration modes of these strings is one that has exactly the properties expected of the graviton, the hypothetical quantum of the gravitational field, the particle that would carry gravity in quantum theory. This was and remains one of the most exciting features of string theory. It automatically and unavoidably contains a quantum theory of gravity to be consistent. String theory requires more than 4 dimensions. In the most studied versions, 10 dimensions of space-time, or leven, in the extension called M-theory. The extra dimensions are compact, curled up on themselves, at scales far smaller than any particle or any current instrument can probe. The number of ways the extra dimensions can be shaped is astronomical. Some estimates suggest 10 to the power of 500 different ways of compactifying the extra dimensions, a number with 500 zeros, each giving a different low energy physics, a different set of particle mass and force strengths, a different apparent universe. This is called the string theory landscape, and it is, for many physicists, both string theory's most exciting feature and its greatest problem. If there are 10 to the 500 possible universes consistent with string theory, how do you predict which one we live in? How do you make testable predictions if almost anything could arise from string theory in some part of the landscape? Is it science or is it infalsifiable? These are genuine and unresolved concerns. String theory has not made a single prediction that has been confirmed by experiment. That could not also have been predicted by simpler means. This does not mean it is wrong. It may be the correct theory of everything waiting for us to understand it well enough to make testable predictions, or it may be a beautiful mathematical structure that is not the theory of our universe. We don't know. Loop quantum gravity, the main alternative to string theory, is loop quantum gravity, LQG, developed primarily by Carlo Rovelli and Lee Smolin. Loop quantum gravity does not try to unify all forces, only gravity with quantum mechanics. The key idea is that space itself is quantized. Space is not a smooth, continuous fabric, but is made of discrete, indivisible chunks, the smallest possible units of space, called spin networks or spin form. At the Planck scale, about 10 to the power of minus 35 meters, a scale at which the quantum nature of space becomes relevant. In loop quantum gravity, space is made of these discrete units. Volume comes in lumps, area comes in lumps. You cannot divide space indefinitely. At some point, you hit the bottom. the Planck length, the smallest possible distance, the pixel size of the universe, time, in some versions of LQG, is also discrete, coming in Planck scale moments. The smallest possible thick loop quantum gravity has also made few confirmed experimental predictions, though it is an active research program with some potential tests in observations of the cosmic microwave background or in the statistics of gamma ray bursts from distant galaxies. The honest situation, we do not have a confirmed theory of quantum gravity. Both string theory and loop quantum gravity are serious, mathematically sophisticated research programs with dedicated scientists working on them, and both have potential virtues and significant problems. The question of how to unify quantum mechanics and general relativity may be the hardest scientific problem humanity has ever faced, and it remains genuinely open. The arrow of time revisited. Why is the past fixed and the future open? We mentioned in the first part the arrow of time, the question of why time has a direction, why it flows from past to future and not from future to past. I want to return to this and go deeper because it is one of the deepest and most personal questions in physics. The laws of physics, as we currently know them, are almost completely time symmetric. If you filmed almost any physical process at the molecular level and played the film backwards, the reversed process would also be a valid physical process, obeying all the laws. A single gas molecule bouncing off a wall played backwards looks exactly like a single gas molecule bouncing off a wall. Both forward and backward obey Newton's laws. And yet, the macroscopic world is deeply asymmetric in time. If you film a drop of ink spreading through water and play it backwards, it looks completely wrong. Ink doesn't spontaneously concentrate itself. Eggs don't unscramble. Broken glass doesn't reassemble. Heat doesn't flow. From cold to hot, the past is fixed. The future is open. The universe has a direction. In time, the standard explanation is entropy, the second law of thermodynamics. Entropy, the measure of disorder, or more precisely, the number of microscopic arrangements consistent with the macroscopic state always increases or stays the same. Over time, the explanation is probabilistic, not fundamental. There is nothing in the laws of physics that prevents ink from spontaneously concentrating, but the number of states with the ink spread out is astronomically larger than the number with the ink concentrated, so overwhelmingly that in practice we never see the concentrated state arise spontaneously from the spread out state. But this raises a deeper question. If entropy tends to increase, why was it so low? In the past, the Big Bang began in an extraordinarily low entropy state, an almost perfectly uniform, hot, dense state with very little structure, almost maximum order. In certain sense, why did the universe start with such low entropy? This question is one of the deepest in cosmology. Roger Penrose has argued that the low entropy of the Big Bang is the most improbable thing in the universe, far more improbable than any specific outcome of any game of chance. The probability he estimates of the universe starting with the particular low entropy initial state that it did is 1 in 10 to the power of 10 to the power of 123. That number cannot be written out, not in full, not in any reasonable space. It is so large that even the number of atoms in the observable universe raised to a power could not represent it. Why was entropy so low? At the beginning is the most profound, unanswered question about time. In physics, some physicists think it points to something special about the Big Bang, perhaps a principle of quantum cosmology that constrains the initial state. Others think it is explained by the multiverse. If there are many universes with many different initial states, we necessarily find ourselves in one with low initial entropy, because that is the only type in which observers like us can exist. Still others think it points to something we don't yet understand about the deepest nature of time and causality. The arrow of time is deeply personal. It is why you remember yesterday, but not tomorrow. It is why you can change the future, but not the past. It is why life has a direction, why stories have beginnings and ends, why everything that has ever mattered to you happens in a specific, irreversible sequence. And the deep reason for that direction comes from a feature of the initial state of the universe, almost 14 billion years ago, that we still don't fully understand. Your personal experience of time, of memory, of anticipation, of regret, of hope is connected in the most intimate way to the deepest, most unresolved question. In cosmological physics, consciousness and physics, the hard problem, physics has achieved extraordinary things. It has described the behavior of matter from the scale of quarks to the scale of the observable universe. It has explained the structure of atoms, the fusion that powers stars, the curvature of space-time, the quantum fluctuations of the vacuum. There is one phenomenon that physics has not explained, has barely begun to approach, and that may require something new, something beyond what physics currently is, to explain consciousness, not the neural correlates of consciousness, the specific patterns of brain activity associated with specific experiences. Those are being mapped gradually by neuroscience. The hard problem, the question of why there is subjective experience at all, why there is something it is like to be you right now, lying there, listening, feeling the surface beneath you, hearing these words, having the particular quality of experience that you are having. This question was named the hard problem of consciousness. by the philosopher David Chalmers in 1995, and it is proven extraordinarily resistant to solution. The explanatory gap. Consider what neuroscience can tell us about the experience of seeing something red. It can describe the photoreceptors in the retina that respond to light of a specific wavelength. It can trace the neural signals through the optic nerve to the visual cortex. It can identify the specific neurons that fire when you see red. It can describe the binding of these neural signals into a coherent visual representation. What it cannot explain is why all this processing gives rise to the felt quality of redness, the particular subjective experience of seeing red versus seeing blue versus seeing nothing. The processing could, in principle, be exactly the same, and there might be no subjective experience at all. A philosophical zombie, the same physical processes, no inner experience, nothing. It is like, to be, why isn't that what we are? Why is there experience at all? No one knows. There are many proposed approaches to the problem. Some physicists and philosophers think consciousness arises from certain type of information processing, integrated information theory, and similar frameworks try to make this precise. Others think consciousness may be more fundamental than physics currently assumes. Panpsychism, the view that some form of experience is a fundamental feature of reality at every level, not something that arises only in complex brains, has been seriously defended by some philosophers. Roger Penrose and Stuart Hameroff have proposed that consciousness is connected to quantum gravity effects in structures within neurons called microtubules. This is speculative and not widely accepted, but it represents the willingness of some physicists to take the problem of consciousness seriously as a physics problem. Most neuroscientists think consciousness will eventually be explained by neuroscience as a product of complex brain processes without requiring any new physics. The honest position is that we don't know. The hard problem is genuinely hard, harder than anything else physics and neuroscience have so far faced, and the fact that you are experiencing this moment right now is among the most mysterious and the most certain facts in the universe. Information, the fabric of reality, a theme that has emerged in physics over the past few decades, is the deep role of information. It from bit, said John Wheeler, one of the great physicists of the 20th century, coiner of the term black hole. He meant that perhaps at the most fundamental level, reality is made of information, not matter, not energy, not fields, but information. What does this mean? The word information in physics has a specific meaning related to, but not identical to, its everyday meaning. In physics, information is roughly the number of binary choices needed to fully describe a system, how many bits, how many yes or no answers it would take to specify the exact state of something. The black hole information paradox, one of the most important arguments for the fundamental role of information in physics comes from black holes. When matter falls into a black hole, it carries information about what it was, its exact quantum state. That information disappears behind the event horizon, never to escape. But in the 1970s, Stephen Hawking showed, using quantum mechanics applied near the event horizon, that black holes are not completely black. They emit radiation, now called Hawking radiation, and they gradually evaporate, losing mass over enormous timescales until they disappear completely. The problem, Hawking radiation, as Hawking originally calculated it, is purely thermal, random, carrying no information about what fell into the black hole. If the black hole completely evaporates and the Hawking radiation carries no information, then the information about what fell in is simply gone. But this violates a fundamental principle of quantum mechanics, the principle that information is conserved, that the complete quantum state of the universe evolves in a way that preserves information, never destroys it, never creates information from nothing. So either quantum mechanics is wrong about information conservation, or Hawking's calculation was wrong, or something happens at the end of black hole evaporation that retrieves the information. This is the black hole information paradox, and it has been one of the central puzzles of theoretical physics for 50 years. Most physicists now believe that information is not destroyed, that it is somehow encoded in the Hawking radiation in subtle correlations, that Hawking's original calculation was too simple to capture. In 2022, a calculation using a new approach called the island formula showed that in principle, information could be recovered from Hawking radiation by the time the black hole is completely evaporated, exactly when quantum mechanics says it should be. This is not a full resolution. We don't yet know exactly how the information gets into the radiation, what mechanism encodes it, but it is progress. The black hole does not destroy information. The holographic principle, the black hole information paradox, led to one of the most striking ideas in contemporary physics. The holographic principle, the maximum information that can be stored in a volume of space, is not proportional to the volume as you might expect. It is proportional to the area of the surface surrounding that volume. This is called the Bekenstein bound, and it implies something extraordinary. Everything that can happen in a volume of space can be encoded on the surface. Surrounding it, like a two-dimensional hologram that encodes a three-dimensional image. Juan Maldacena in 1997 showed in a specific mathematical context that a theory of gravity in 3 dimensions is exactly equivalent to a quantum field theory without gravity. on the two-dimensional boundary of that space. This is the ADS CFT correspondence. One of the most important results in theoretical physics. In the past 30 years, it suggests that gravity may be emergent, not fundamental, that it arises from the quantum entanglement of a theory that lives on a boundary that space itself and gravity may be encoded in and emergent from quantum information on la surface, that the three dimensions we seem to move through might be a kind of holographic projection of a deeper two-dimensional quantum reality. This is not established. It applies directly only in specific mathematical contexts that may or may not describe our actual universe, but it is among the most profound and most active research directions in fundamental physics. The universe as information. The theme that runs through all of this is that information may be more fundamental than matter or energy, that the laws of physics are laws about how information behaves, and that the physical world may be, in some deep sense, made of information. This is a hypothesis, a research program, not a settled conclusion, but it points toward a possibility that the world at its most fundamental is not made of stuff, but of pattern, of relationship, of information, what we don't know, the honest inventory, let me be honest, about what we don't know. Because this is as important as what we do. We don't know what dark matter is. 27% of the universe, detected only gravitationally, completely unknown. In its nature, despite decades of increasingly sophisticated experiments, we don't know what dark energy is. 68% of the universe, the dominant component causing the accelerating expansion, completely unknown, despite being the thing that determines the ultimate fate of everything. We don't know how quantum mechanics and general relativity are unified. The two most successful theories in physics are mathematically incompatible, and we don't have the theory that contains both. We don't know why the universe started in a low entropy state. We don't know what caused the Big Bang or what preceded it, or whether that question even makes sense. We don't know why the constants of nature have the values they have, why the universe is tuned for complexity. We don't know what consciousness is or why there is subjective experience at all, or how physical processes give rise to the felt quality of experience. We don't know whether there are other universes. We don't know whether the universe is finite or infinite. We don't know whether information is truly fundamental, whether space-time is emergent, whether the three dimensions we experience are all there are. These are not small gaps in an otherwise complete picture. These are enormous questions that define the frontier of human knowledge and lie beyond it. Physics is not finished. It may be less than halfway to a complete description of reality. If complete description is even possible. This is honestly held, not as a discouragement, but as an invitation. The universe is not fully understood. The questions remain open. The possibility of discovery is real and present for anyone willing to do the work. The unreasonable effectiveness of mathematics. Why does math describe reality? There is a mystery at the heart of physics that is so familiar, we rarely notice it. Mathematics works. It describes physical reality with extraordinary precision. The physicist Eugene Wigner wrote a famous essay in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He noted that mathematical structures developed by mathematicians, often purely for abstract reasons with no thought or physical application, turn out later to perfectly describe physical reality. The mathematics of curved spaces, developed in the 19th century by Riemann for abstract mathematical reasons, was the mathematical framework that Einstein needed 50 years later to formulate general relativity. The mathematics of group theory, developed in the 19th century to study the symmetries of abstract mathematical objects, turned out to be exactly the right language. For quantum mechanics and the standard model, the mathematics of Hilbert spaces, abstract infinite dimensional mathematical spaces, is the natural setting of quantum mechanics. Why? Why does mathematics describe physical reality at all? Why should the universe follow mathematical laws? Why should abstract structures invented by human minds for aesthetic reasons map onto the deep structure of reality? There is no agreed answer to this question. Some physicists think the universe is mathematical, that reality is made of mathematics, that there is no distinction between the mathematical structure and the physical world. Max Tegmark has defended this view explicitly in what he calls the mathematical universe hypothesis. Others think mathematics is a product of human minds, evolved to understand the world, and that the apparent mathematical structure of the world reflects something about how minds work, not something about fundamental reality. Still others simply accept the mystery and continue using the mathematics that works. Whatever the explanation, the fact remains that the universe follows mathematical laws with a precision and consistency. That is itself one of the most extraordinary features of reality. The question beneath all questions: why is there something rather than nothing? We are at the edge of what physics can say anything about. At the beginning of the universe, there was something, not nothing, even if the Big Bang was the beginning of time itself. There were the laws of physics, the mathematical structure that governed what happened. Why? Why are there laws rather than no laws? Why is there something rather than nothing? This question may not have a scientific answer. It may lie beyond what science can address. In principle, physicists like Lawrence Krauss have argued that the universe could arise from quantum fluctuations of the vacuum from nothing, but critics point to that quantum fluctuations of the vacuum are not nothing. The vacuum has a mathematical structure, laws governing it, quantum mechanics already in place. Why are those laws in place? Why is there a vacuum at all rather than pure nothingness? This is where physics gives way to philosophy or theology. Or silence. The honest answer of physics is that it cannot currently address this question. Physics describes how the universe evolves. Given that there is a universe with certain laws, the question of why there is something rather than nothing, and why the something that exists follows the specific laws, that it does lies beyond the current reach of physics. This is not a failure. It is honesty about limits. The most important thing scientists can do is know what they know and know what they don't, coming home back to your hand. We started this story with your hand, 7 octillion atoms, mostly empty space, and yet solid, capable of touching and holding and making things and being held. We know more now about that hand. Those atoms are not particles sitting at specific locations. They are excitations of quantum fields that fill all of space, localized temporarily into what we call matter by the specific conditions of the early universe. The electrons in those atoms are probability distributions, not little balls smeared across the orbitals of the quantum mechanical wave function until and only if you measure them. The nucleus at the center of each atom is held together by the strong force carried by gluons, in a way so non-linear that no one has yet mathematically derived the properties of the proton from first principles, despite decades of trying the solidity of your hand against the surface you're lying on is the Pauli exclusion principle, quantum rules, preventing electron clouds from merging, not matter, being full of anything. The weight of your hand is gravity, the curvature of space-time by the mass of the earth guiding the atoms in your hand along geodesics through curved space-time toward the surface. The warmth of your hand is the kinetic energy of atoms vibrating in their quantum states above absolute zero, a temperature they can never reach because of the 0-point energy guaranteed by the uncertainty principle. The atoms themselves were forged in the cores of stars billions of years before the Earth existed, scattered when those stars exploded, gathered by gravity into the cloud that became our solar system, incorporated into the Earth, into life, into you. Your hand is the universe looking at itself through the particular temporary quantum mechanical arrangement that is you. What physics cannot tell you, Physics can tell you the structure of atoms, the forces that govern their interactions, the fields that permeate all of space, the curvature of space-time, the quantum uncertainty at the heart of reality, the arrow of time, and its origin, the beginning of the universe, and the limits of our knowledge. Beyond it, physics cannot tell you why the experience of being you feels the way it does, why the particular quality of consciousness that you have right now exists rather than nothing. Physics cannot tell you what to do with your life, how to be kind, what to love, what to work toward, what is worth your limited and precious time. Physics cannot tell you whether your life matters, though it can tell you that you are made of matter that has been part of the universe for its entire existence and will continue to be long after the particular arrangement that is you has dissolved back into the world. What physics offers is not the meaning of your life, but a context for it, a context of extraordinary scale and depth and strangeness that makes the ordinary rather more interesting than it usually seems. When you touch something, you are experiencing quantum mechanical repulsion between electron clouds mediated by the electromagnetic field, which is a quantum field filling all of space. Since the beginning, when you breathe, you are taking in molecules that were part of every living thing that has ever breathed on this planet since life began 4 billion years ago. When you look at the sky, you are seeing light that has traveled through curved spacetime from sources billions of light years away, carrying information about a universe that will look different after any future civilization has lost the ability to see it. We are living in the privileged moment when it is all visible, all knowable, at least in principle, when the questions are clear, even if the answers are not the closing, the universe thinking about itself. Tonight, we've gone as deep as physics currently goes. We've looked at quantum field theory and the Standard Model, the most successful theory in the history of science. We've looked at the interpretations of quantum mechanics, the century-old debate about what the theory means. That has not and may never be resolved. We've looked at the attempt to unify the two great theories of the 20th century and the deep difficulty of that project. We've looked at information and the possibility that it is more fundamental than matter or energy, that the universe may be made of pattern rather than substance. We've looked at the mystery of consciousness, the hard problem that physics does not know how to approach, and we've looked at the question beneath all questions: why is there something rather than nothing? Which physics honestly cannot answer. What remains when you set all of this down, when you stop trying to hold all the ideas at once, what remains is what was always here. Your body on this surface, in this room, at this time, in this particular corner of the universe. the atoms in your body following the laws. We've been discussing perfectly, as they always have, as they always will. The universe did not need you to understand it, to follow these laws. It followed them for 13.8 billion years before you existed, and will follow them for an incomprehensible time after. But you understand a little. You've spent this night with the deep structure of reality, with the rules that govern everything, from quarks to galaxy clusters, from the first fraction of the first second of the universe to this moment now, and the fact that the atoms in your brain can represent, can model, can in some sense contain a description of the quantum field from which those very atoms are made. That is perhaps the strangest, most beautiful, most unlikely thing in the entire universe. The universe made something that can understand it a little, and it used its own matter to do it. You are the universe thinking about itself right now, tonight, in this room, through the particular temporary conscious arrangement that is you. The physics doesn't stop while you sleep. The fields keep vibrating. The space-time keeps curving. The quantum fluctuations of the vacuum keep flickering in and out of existence. The expansion of the universe keeps accelerating. The arrow of time keeps pointing in the same direction it always has, toward tomorrow, and you will wake up in a universe that is exactly as strange, exactly as beautiful, exactly as mysterious as it is right now. And you will carry with you something you didn't have before, a slightly deeper acquaintance with the rules that the universe is to be itself. And maybe that changes something about how you see your hand in the morning. Close your eyes now. The physics has you